Hello, everyone. Yeah, today I will try to explain non-native field arithmetic. It's a little bit low-level slide, but I hope I can keep you with me. Yeah. So basically, why we are using non-native field arithmetic, or why it's needed. Okay, basically, this is usable when we deal with proof aggregation. When we want to deal with proof systems, we use scalar field. And when we deal with group operations, we use base field. So we have two different fields, and we want to, our native field is smaller than our wrong field. And that's why when we want to aggregate created proofs, we need to use such a way to crack down our wrong field, so we can use it as a native field. That's the main idea here. Here in the photo, you can see that we have a field, and fields are actually we define a field, then we define a field, and then we construct elliptic curve from this field. And because why we are using elliptic curves? Because they provide us a groups, and we can do group operations after that. Yeah, this is the main idea, that we are first defining a field. The first defined field is wrong field, and we are defining our elliptic curve from wrong field. Okay, you can see here that we have, in purple, we have field, and after field, we are defining our elliptic curve from this field, and we have this group, and we have several operations in groups, point addition and point doubling. So point addition and point doubling naturally gives us scalar numbers after a point, because if you want to take point P and add another point P, you get 2P. So that 2 is our scalar number, and with this way, we are getting our scalar field. And after that, we can use scalar multiplication on our field. This is the basic order. Yeah. And here, the first purple is our wrong field, as I told, and the native field that we create from group operations that naturally occurs, and that field is smaller than our wrong field. Yeah. Now we will use two different methods. One is Chinese remainder theorem, and other one is residue number system. So we will use Chinese remainder theorem to constrain equation to check validity. This is pretty important. I will show the low-level part of this. On the other hand, RNS will be used for the calculations. Yeah, we can start with RNS because I think it's a little bit easier. So basically, you can see that there's, if we use mod 5, we have 0, 1, 2, 3, and 4. You can't get 5, 6, or 7 because it will automatically, you will take the mode and it will be 0 or 1 or 2, etc. But that doesn't mean that we don't have these numbers. We can represent these numbers in a way, and we can keep the data, but still we can lower, and we can use this in our calculations. So why this is important? Because we are inside fields, and fields has boundaries. They are like prime numbers. And yeah, we will keep this in mind. And in the future, that when we do operations, like if we have 12 mod 5, we will know this is still 12, but we will represent this as a number 2. So Chinese remainder theorem. This is a pretty nice theorem, actually, because this theorem gives us a solution to a system of linear congruences in relatively prime moduli. So basically, we can see in the example that we have x in 5, in 7, the represented number in 5, 7, and modulus 11, right? like 2, 3, 4. So we can use this tree number and get a number x that satisfies this equation. In this case, it's a little bit long example, but in this case, 367 mod 385 is our x that satisfies that tree equation. So this way, we can use different numbers and keep data and build our original, check our constraint with this way. And we can know that we have different, like we will use wrong field and native field, 2 different modulus, and we can use this theorem to check constraint that wrong field number is satisfying inside native field. Okay, yeah, this is little bit starting, it will a little bit mathematical part, and yeah, we will implement algorithm basically to show you how we do that. Yeah, we have several notations here. Wrong field modulus, we show it as a P, and we have native field as N, and we will have binary field 2 over T. I will show this to you in the next slide. Yeah, just to keep in this mind. We can do multiplication, addition, division, and all of the operations, but I will show addition because it is a little bit simpler and yeah, easier, I think. So here's a formula that we need to follow this. It's actually very basic, A plus B. We are doing normal addition, and Q times P plus R. R is our remainder or result, and P is our moduli, and Q is coefficient, how much time that we wrap around our modulus. So in this way, this equation should be 0. If it's not, we can say that there is something wrong with this calculation. Okay, we need to calculate 4 different things to check this calculation. Yeah, we can start with coefficient here. Oh, sorry, before that, I need to explain at binary field. We will use this in Chinese remainder theorem. This is so our native field is smaller than our wrong field, as I told before several times. So we need a helper field to leverage our native field. So 2 over T is, this should be very specific number to multiply with, we need to multiply with our native field, and it should be bigger than P squared plus P. Because like P squared is coming from, you can see that Q times P, we have Q times P. If Q is the biggest number in P, it will be P squared, and if remainder is the biggest, it will be P, so P squared plus P. It should be bigger than that, so we don't lose any data. We already implement this in our project, and in our project, we use T as 272. This number can be divided to 68 bits of 4 limbs. Yeah, what is limbs? So, as I told, we need to use some method to crack down our big number and use this binary field to keep data in each limb, and with this way we can fill our numbers inside each limb and don't lose anything. So you can see in the first limb we are keeping the first 68 bits. In second we are keeping other 68 and other 68, so we will have 272 bits. And it's already bigger than our wrong field because our wrong field is 254. Actually, native field is 254 as well, but it's a little bit smaller. So yeah, with this way, we are guaranteeing that we have bigger field and bigger space for our numbers. So yeah, we can start with coefficient and result. This is actually the easiest one to calculate. So in addition and subtraction, coefficient cannot be bigger than 1. There is a reason for that, because if you take the maximum number and add the maximum number, you will just wrap around the modulus 1 time. And you can't go more than 1. So that's why we are just keeping it in a short form, and we are typing 1 or a 0. But if you use this algorithm in multiplication or division, you can get very big numbers. So yeah, this is just for addition and subtraction. Sorry, for the result part is actually after that we wrap around or not. The result that we get basically is our result, and coefficient will be just 1 or 0. So intermediate values, yeah, this is the part that it's it will be a little bit lower level. So yeah, this is needed to check our Chinese remainder part, actually. So we will calculate this, and after that, we have such a strange way, like we are doing this for each limb, and yeah, we are using negative modulus inside native, we are using binary field inside negative wrong field, and we are multiplying with quotient, and yeah, we are calculating these intermediate values. It's a little bit complex. You don't, have to understand that deep down, but basically, with this way, we are getting each limbs and keeping data that we have a number that is bigger than our field. If it's bigger, that we can reconstruct, or we can know that that number is exactly the number that we write in the first part. So if it's get wrapped around, we will still know that we have these values, and we can say that, yeah, we still keep the original data, and we can do constraints on them. Yeah, after that, we have residues. Yeah, in residues, it's actually a little bit different, I can say, but let me explain left shifters and right shifters first. We are using this a lot. Basically, left shifters is if you take the second one and multiply with one limb, it will take that limb to the upper level. So if you use these 4 left shifters, if you multiply with your number that you crack down inside limbs, it will reconstruct your original number, but it will be in native field. So if it's bigger than your native field, you will lose data. So that's why we need to keep these intermediate values on our pocket. So we know that, yeah, it's wrapped, or we can check constraints that it's calculated correctly in the future. In residues, we are basically taking, each limb from intermediate values, and we are left shifting one time, the second one, so it gets to the up level, and for result part, we are doing same, and we are following this formula. And yeah, at the end, we get such a number with 2 limbs, not 4 limbs this time. Residues is our reduced half size of the original limbs. If you have 8, it will be 4, but in our case, we have 4, so it will be length, limbs will be length of 2. And yeah, we will follow this formula to build our residues. It's still, yeah, a little bit complex, but we need to use this in the future calculation. I will show you right now. Yeah. So at the end, we are coming to native constraints. And yeah, native constraints are actually very efficient. You can do this very easily. So we are just taking a plus b that I showed you in the first place, the formula. We are just taking the right side to the left side, and we are checking that if it's 0 or not. If it's 0, we say, okay, this is calculated correctly, but we are checking this in native field. So we say that in a native part, this constraint is satisfied, and we can go check the second part of our constraint, which is Chinese remainder theorem, binary constraint. This is the actually important part for this. Yeah, we need to follow this formula. So we build residues and intermediate values and residues from them, and we are doing the opposite, like we are doing reverting it and checking that if it will satisfy 0 or not. So this is basically the reverse calculation of residues, and if these results returns 0, then our constraint satisfies. Yeah. Yeah, I would like to thank my team, Ariel Gebizin and Sait İmamoğlu, who helped to review this. And yeah, before I finish, I actually forgot that I should mention this. Yeah, we are doing these operations. So yeah, I have a little bit time. So we are doing these operations because in rollup systems, ZK rollups, if you ever heard about it, so we are creating zero-knowledge proofs, and after a point, zero-knowledge, yeah, they are very cheap and they are not taking too much size, but there's a good thing, they are always constant, so if you want to merge proofs, you will get a constant value again, right? So with these formulas and, sorry, if you like follow this non-native field arithmetic to create it down, and after you build proofs, you merge that proofs again and again and again, you will just have one little constant size proof, and it will have maybe like you can put inside like millions of proofs. It will take a lot of time in prover side, but in verifier side, it will just take a second to verify that, okay, this rollup, all of these proofs are correct. This is why we are using this. This is actually pretty important for future of the ZK. And yeah, that's all. Like I would like to, if you guys have any questions, I would like to answer and maybe show you, maybe help you more about this topic. Yeah, it was a little bit extreme, I think. Yeah. So as I told, you guys, if you don't know what ZK is, I can explain a little bit more maybe to you. So ZK is zero knowledge. Actually, is pretty nice way to verify that you know something, and basically they are telling that that you know something, but you are not leaking any information what you know, but you can convince someone that. Yeah, they will say, okay, this guy, or I don't know, they are telling the truth. So we can use this in our Ethereum network. So in the future, it will be constant size proofs, and you will just verify them in a short time. But the problem is, the creating proofs are actually a little bit expensive. So like you can put, I don't know, trillion of proofs. Like you can put every proof that you created inside your only one proof, but it will take a lot of time from your prover part. That's the actually bad part of the ZK. Yeah, that's all. If you don't have any questions.